Now, the first key area of physics that we study is known as kinematics. Kinematics is the description of motion. We want to know where something is, how fast it's going, and how quickly it's changing that speed. To begin with, we're going to make a simplification. Specifically, we're going to treat all the objects as particles. We're not going to worry about their extended size. We're not going to worry about whether they're rotating or stretching or breaking apart. Each of those are things that we will discuss at a later point. But right now, we're just going to talk about the overall motion of the particle. And the first part of understanding how something moves is understanding where it is. That means we need to be able to describe an object's position. It turns out that describing an object's position is not trivial. We need to know where is it compared to some other object. So in other words, first, I need an origin, some reference point to compare it. And second, position is the first of many quantities we will study, which are known as vectors. As we study in physics, we find that many quantities only require us to tell how big that quantity is. Time, temperature, mass. There is no sense of direction with any of those. However, certain quantities, such as position, speed, velocity, force, and many others, do have a very definite sense of direction. It's a very different thing to be traveling 60 miles per hour with traffic than be traveling 60 miles per hour against traffic. So direction is very important in these particular instances with these quantities. We call those quantities that depend on direction vectors. Now, a vector relies very heavily on how we choose our coordinate system. However, we do have a number of ways of dealing with this. So when we draw a vector, when we represent a vector quantity on a page, we draw it as an arrow. An initial point at the tail and the head at the end. There's an arrow pointing the direction that the vector goes, and the length of the arrow is proportional to the magnitude of the vector we're describing. If we're talking about an actual length, it may be the actual length of the vector, or it may be some proportion to it. If we're talking about speed or acceleration, it has to be a proportionality because a length is not a speed. As I said, the length represents the magnitude, and the direction represents the direction of the vector. Generally, if I'm using a vector in an equation, I will put this little arrow over the top of the symbol to remind you that it's a vector. If we're dealing with just the magnitude of that same quantity, I may drop the arrow, and that tells you I'm talking about the magnitude of this particular vector. One of the standard ways we write vectors is to give the magnitude and the direction. This is known as the polar form of vector notation. If I have a vector that is 0, well, it's just represented by a dot, and obviously it has no direction, or we simply say its direction is arbitrary. The next question is, what do we mean if we say that two vectors are equal to each other? Well, two vectors being equal means that they begin and end at the same spot. It means that they have the same length and the same magnitude. They don't have to be in the same position. So if we look here, vectors A and B are considered to be equal to each other. There are a number of other ways of representing vectors, and I'll just talk about them very briefly here. Later, when we get to chapter 4, we will start talking about motion in 2 and 3 dimensions, and we'll need to work more with our vector notation. But we want to give you a sampling of it right now. The first thing we do is we talk about Cartesian unit vectors. In other words, sometimes we want to describe a vector in terms of how much it goes in the x direction, how much it goes in the y direction, and how much it goes in the z direction. We describe that in terms of these unit vectors. They are vectors whose length is 1, not 1 of some unit, just 1. They are I hat, j hat, and k hat in the x, y, and z directions respectively. So I could describe a vector not in terms of its magnitude and angle, but instead in terms of how far do I have to go in the x direction, and then how far do I have to go in the y direction to get from the beginning to the end. These are known as components of a vector, and I can write the vector A as its x component times I hat plus its y component times j hat. Or sometimes I will just write that as an ordered pair. Whereas the other one was considered the polar form, this is considered the Cartesian form. The sign of the components gives us information about the direction of vectors. So vector C has a negative x component and a positive y component. Vector B has a negative y component and a positive x